Okay, thank you so much for having me here. My name is Shreya Anand. I'm an LSST DA Catalyst Fellow at Stanford University, and I'll be talking to you all about computing hurdles in the wide field target of opportunity searches, mainly focusing on gravitational wave searches with ZTF, but mostly talking about Rubin actually. So this is the way I like to think about challenges in conducting counterpart searches. Um, it's mainly it's mainly like searching for a needle in a haystack, right? So you have several terabytes, maybe 20 terabytes a day, in the case of Rubin, to parse through and to find one single counterpart that is associated with a gravitational wave event or any other external trigger. And in the case of neutron star bearing events, we expect the counterpart to actually be very faint, fast fading, and red. So here you can see the light curve of 170817 decays very fast in the bluer bands. It's a bit longer lasting in the redder bands, but the point is you don't have much time to actually identify an associated counterpart. And the third issue is that the sky localizations that we expect from LBK events tend to be extremely large and spanning large swaths of the sky. So it makes it very difficult to actually find a counterpart. Fortunately, we have many wide field facilities that are capable of doing this follow-up, and it's a combination of wide field of view and depth that are really key to finding these associated counterparts. So today I'm going to be talking about ZTF and Rubin, LSST, but I'll also mention DCAM as well. So ZTF has a field of view of 47 square degrees and reaches a median depth of G of 20.5 mag. LSST goes much deeper, G of 25 mag roughly, but has a bit of a smaller field of view. And then DCAM has a smaller field of view than that, 3 square degrees, but reaches a depth of 24th mag. And I'll mention DCAM in the context of the recent follow-ups that we performed with LSST and the need to do cross-survey image subtraction. So the first step here is actually trying to conduct efficient observations of the entire sky map in question. So here's the sky map of GW 190425. As you can see, it spans a wide area, and this shows the ZTF coverage of this particular sky map. The way the coverage is performed involves a complex optimization problem that takes into account the probability coverage within the sky map, observable fields, moon distance, air mass, and other factors in order to determine the order for observing these particular fields that overlap with the localization. And once that scheduling and observations have been performed, then comes the process of actually finding these candidates. So here you can see the main way that we try to identify these new candidates is through the process of difference imaging. So you can see a new image here with ZTF shown here. The crosshairs are the position of the expected new transient. You can see that that transient is not present in the reference image. And then once you perform subtraction between the new image and a previous image that was taken, you're able to get a clean subtraction. And then there needs to be initial filtering that happens to determine whether or not this transient is actually real and perhaps astrophysical. So the way this is done is by using machine learning algorithms to determine whether a point source is real or bogus, to determine whether it is a star or a galaxy, check whether there's no point source underneath, no bright star that could be bleeding into this into the pixels here. and then rejecting things like moving objects. And so we finally get to our list of initial candidates. But further bidding needs to be done in order to determine whether those candidates are actually consistent with what we expect a kilonova to behave like in the case of a gravitational wave search. So, so here you can see our ZTF coverage of a particular event, S230627C. And the various kilonova candidates that have been filtered through. So the different steps that we took to perform filtering include spatial and temporal coincidence with the gravitational wave event, filtering on light curve properties, so checking whether something is reddening like a kilonova, checking whether or not it is too slow to be consistent with a kilonova, and then filtering out additional types of contaminants that we expect from our follow-ups that we can reject, so that we only focus our valuable follow-up resources on candidates that we believe to be looking and evolving very kilonova-like. So this is a process for filtering and identifying candidates that we use with ZTF. Now I'm going to shift gears a little bit and talk a little bit about Rubin and how we have been conducting these follow-ups with Rubin. So just to give a little bit of context, in 2024, the MMA community, or a large portion of the MMA community, came together to draft recommendations for Rubin target of opportunity follow-up. And the punchline here is that we were able to secure up to 3% of Rubin's time for target of opportunity follow-up, and outline the various science cases and the strategies that we want Rubin to adopt for conducting its TOs. So this has since been endorsed by the Survey Cadence Optimization Committee. And these are the main science cases that are covered in the Rubin TOO program. So these include gravitational wave events, hazardous asteroids, high-energy neutrinos, and other kinds of rare events. But I'll focus on the gravitational wave aspect of this. Just a little bit more background, the way Rubin target of opportunities work is that we initially ingest alerts through SIMA, which is the scalable infrastructure for multi-messenger astronomy. And SIMA listens to and receives alerts from the LBK, IceCube, Super K or SNUs, and JPL Scout for asteroids. And once these external triggers have been ingested, each alert is parsed for alert quality criteria. So as spoken about in the previous talk, we have set some strict triggering criteria for each of these alert types. And only if they satisfy these triggering criteria, such as passing a particular false alarm rate or other properties, we would actually trigger on it. Otherwise, it would be rejected. And so when an alert passes these quality criteria, then it's automatically ingested into the Rubin engineering facilities database. And from there, it's sent to the Rubin scheduler, which proceeds to create an observing strategy for conducting the observations for that night. And after that, it's executed by Rubin and then passed on to the prompt processing pipeline for analyzing these observations and creating the alerts. In the case that an alert does not pass these automated triggering criteria, there is a Rubin Target of Opportunity Advisory Committee that exists that has the ability to decide or recommend whether to observe an event that did not pass these criteria for various reasons. So I'm going to talk about two specific follow-ups we performed with Rubin during the commissioning and early operations period, and what we actually learned from these follow-ups and challenges for the future. So the first the first follow-up that we actually performed was that of 3I Atlas, which is an interstellar object. I'm not going to talk about that at the moment, but that was the first follow-up that was performed. The second follow-up that we performed was that of S250725J, a binary black hole merger candidate. This was a candidate that was extremely well localized, so therefore passing our nominal automated triggering criteria. It was at a distance of 380 megaparsecs, and we started observations 4 days after the merger and took 9 Rubin pointings that covered 94% of the credible region. So here you can see Rubin pointings covering the binary black hole merger sky map, which again was very well localized. And we performed a filter strategy in the U, R, and I bands, reaching a depth of about 24th magnitude in R. So the main challenge that we encountered after performing these observations was that there are no existing Rubin templates in the region. This is because Rubin is again in commissioning and early operations phase and hasn't had a chance to build templates of the entire sky. This will actually continue to be a significant challenge during IR1, the next LVK observing run that is coming up later this year, where we won't have complete template coverage. So we had to run an offline custom image processing task. This was developed by 2 of our staff members at Rubin to create DCAM templates from archival surveys that were covering that region and reaching a similar depth to that of Rubin. And then these were run through the LSST standard data release production pipelines to get the difference images and the subsequent photometry on the alerts. So we were able to initially demonstrate our success that the pipeline works. And the way we did this was by looking at previously reported candidates and seeing whether we could successfully recover them. So here's one particular example of a candidate that was reported by DCAM by a different follow-up campaign of this particular event. Here you can see the new transient in the DCAM image, and then on the upper panel, the Rubin image, which shows the detection of the same transient in Rubin. So we're able to successfully recover something that we believe to be astrophysical. But we encountered several issues due to astrometric matching and the fact that we had to observe a very low galactic latitude portion of the field, which resulted in many stars that were contaminating our difference images. And a further issue was that we were not able to get late time follow-up as according to our observing strategy due to poor weather at the summit and other commissioning priorities. So we weren't able to actually do a full analysis of the Rubin data and follow-up for this event and report new candidates that were not previously reported. This changed with our subsequent follow-up of this subsolar mass merger candidate, S251112CM. This was localized to 1681 square degrees. So in contrast to the previous event, this is extremely poorly localized, at least from the Rubin perspective, but it's much closer in terms of distance. So given the exceptional nature of this event and the fact that it had a strong chance or had a chance of producing an EM counterpart, the Rubin leadership and the TO advisory committee together decided to recommend triggering on this event. We're able to cover 39% probability with Rubin, which corresponds to the southern lobe of this large sky map, which also has some probability in the northern hemisphere. And we performed 4 epochs of observations according to the plan. This allows us to get a really nice baseline for the transients and to more robustly distinguish kilonovae from counterparts. From contaminants. We reached a median depth of about 24th mag in G-band. One thing that was unexpected was that we were able to achieve an unprecedented mapping speed covering over 800 square degrees in 2 bands in less than 3 hours. So this was actually better than we had expected in the past and gave us a better idea of Rubin's TOO capabilities. You can also look at these recent papers which talk about other follow-ups that were conducted of this particular GW event. So once we performed the follow-up, we ran it through our same custom image processing Rubin minus DCAM processing pipeline, which yielded 8.7 million alerts. This is a lot more than we typically get with our ZTF follow-ups or other wide field follow-ups. And largely this is due to the depth, but also using DCAM as a template here. So first we implemented some basic image quality cuts, as I had spoken about earlier, to filter out things that we don't believe to be real. And we end up with 160,000 candidates, which is still too many to actually vet by eye. So we have to implement some light curve-based filtering, which requires specifically multi-night detection, multiple detections, and multiple filters. And then we're able to get down to about 5,700 candidates. Only after this step, we were able to do external cross-matching because cross-matching to external catalogs tends to be quite expensive. And once we had rejected things that look like active galactic nuclei, stellar candidates, and asteroids, we end up with 1,300 candidates that we had to visually inspect, which is not too bad, but still relatively computationally extensive. So we end up with a set of GCNable candidates that are relatively digestible and that we're able to disseminate to the community. So I see I'm running out of time a little bit. Sorry. So I just want to say we were able to find some real candidates in our data. As shown here, this is actually a candidate that was first reported by GoTo. And you can see the successful difference imaging of this candidate. So I'll skip over a few slides here, but I wanted to leave you with some of the challenges that we anticipate during future follow-ups with IR1. So the first challenge here is actually being able to schedule observations in large sky maps, optimizing probability coverage, observability, and other constraints, and streamlining our automated triggering. A second challenge here, which I think is one of the most significant challenges, is lack of template coverage during IR1. So previously we had done these image processing offline, but this is something that needs to be run in real time. And we need to also be able to robustly mitigate artifacts in real time. And there are also some challenges associated with getting deeper exposures of than 30 seconds, which could result in various artifacts. So again, artifact mitigation becomes a big issue. And finally, challenges related to alert filtering. So during IR1, the vision moving forward is that since all of these alerts will actually be streaming into alert brokers, we want to implement a universal community filter that will be able to identify all real astrophysical transients within a localization covered by Rubin. But in practice, this requires working with each particular broker and their requirements to implement these filtering. And some of the challenges that exist are actually trying to do archival queries on updated sky maps or filtering to result in a digestible number of candidates that the community can then follow up. So we have lots to iron out in advance of IR1, and I look forward to hearing all your questions. Thank you.
All right. I am on. Thanks, Shreya. We can take questions while Ved is coming up to get set up for the next talk. Is there anyone? I saw hands in the back.
So can you go back to the page where you discussed how many alerts you have and then how many of those are actually real? So there is now the 8.7 million are at what is this per night or per entire running period so far? Per what time period is this?
Yeah, that's a great question. This is over our 4-epoch campaign. But in practice, this is actually over the course of. So we performed 4 epochs that were spaced out over approximately 8 nights
Okay,
of follow-up.
so it's about 1 million a night.
Yeah.
And so then it's about 10. So how many? If you have 1 million a night, how many are actually astrophysical? Because there's different kinds of astrophysical, right?
Yeah, that's a great question. It's a little bit hard to say. The reason being because we implemented these light curve based filtering cuts, right? So we require a minimum of some number of detections. It's possible that there could be some, astrophysical transients there that were only detected once, but we have no way of evaluating whether they look like kilonova if they're only detected once, for example, right? That said, we believe that, these, 70 candidates that we released to the community are high fidelity, astrophysical transients. But it's hard to evaluate how many candidates were potentially missed using these quality cuts.
Thank you.
All right, let's thank Shreya again.